finding direction of B. Direction of B. So for that, as I told you, we are going to use a right hand thumb rule for straight currents. Straight currents means what? That is this one. So we have, so this is a conductor, straight conductor. This conductor is carrying a current I. This conductor is carrying current I in the upward direction. Now we want to find what is the magnetic field direction due to this conductor at a different point. On the left hand side, what is the direction of the field? Right hand side, what is the direction of the field? What is the direction of the field? For that, see, right hand thumb rule. See this, take your right hand. Keep the palm stretched. First you keep like this, and the thumb must be perpendicular to the palm. The thumb must be perpendicular to the palm. Now imagine that we are holding the conductor. Imagine that we are holding the conductor, keeping the thumb in the direction of current. Keeping the thumb in the direction of current. Just see the diagram, how I hold it. This is the direction of current upward. Upward direction current. Thumb is in the upward direction. Then the curled fingers will indicate the direction of the magnetic field line. The curled fingers indicate the direction of the magnetic field line. Means, just see here. See in this case, suppose for example, we are holding the conductor in the palm. Okay, so we are holding conductor in our palm. This is the thumb. Suppose this is our thumb now. And these are the fingers. See this now. See the diagram here. This is our right hand. This is the thumb. Thumb is in the direction of current. And the curled finger, they indicate the direction of the field lines. The direction of the field line. So, just see this now, how it is. On the left, it is coming out of the board. The fingers are coming out of the board. No, lines are coming out of the board. Means the field is out of the plane. The field is out of the plane. When the field is out of the plane, we are going to indicate by a circle with a dot. Like this we will put a dot. That is, it is the field coming out of the board, means out of our notebook. It is coming out of our notebook page. So that is the field. That is the field coming out. This is the head of the arrow. Arrow head will be there, no point. That is the symbol of this one. Now you come to this side, how they are. See, the field is going into the plane. Means when we come to the right side, suppose here the field will be into the board. Then we put a cross like this. That indicate the field is into the plane of the board. That is, it is the arrow tail. This indicate arrow tail. So this is the direction of the field. So whenever you find a field symbol like this, that indicate the field is coming out of the plane, and whenever you find a symbol like this, the field is going into the plane of the paper or into the plane of the board. So that is a way to find this direction for magnetic field by a current carrying conductors, straight conductor. These are all straight conductors, means line currents. We can say these are all line current. But what about circular current? For that, now first what we are going to do is we want to find what is the magnetic field due to a current carrying loop. So first let us find magnetic field magnetic field at center of current carrying loop. Current carrying loop. So that is circular current, we can say. This is also called circular current. Okay. So for that, let us take the circle, means a ring carrying a current. Okay. This is a ring carrying current. Right? Now, the radius equal to small r. Let us say radius equal to small r. Radius equal to r. Okay. Radius equal to r. And it is carrying a current I, say in the clockwise, anti-clockwise direction. Anti-clockwise direction. Current I. Right? Now what we want to find? What is the magnetic induction or the magnetic field due to this current carrying loop at the center, that is O, let us say, at the center O. At the center O. So first what we have to look at now? First we have to draw the position vector. The position vector of the point with the current element. So I am taking, this is the current element now. This is the element what I am taking here. Small element I am taking here. Right. What is the direction of this current element? Tangent drawn at that point. It is the tangent drawn at that point. Am I right? So this is the tangent drawn at that point. Okay. Now, at which point we want to find the field? We want to find the field at the center, isn't it? So what we have to do now? We have to join the center to the current element. We have to draw the, we have to join this current element. We have to join the current element to the center where we want to find the field. So this is our radius. So this is our radius. Right. Now, where is our current element? This is our current element. So what is the direction of this current element? Tangent. This is the direction, isn't it? That is the direction of IDL. So that is our IDL. So this is our IDL. Now, due to this IDL, where do you want to find the field at the center of the loop? At the center of the loop, no. So means we have to join that center to the element. Okay. So to the element. Then what is our theta? Theta is the angle between the position vector of the point with the current element, that is this one. What is this angle? What is this angle? 90 degrees, no, because this is radius and this is tangent, so 90 degree. Then what we have? Apply our Biot-Savart's law. What we have? dB is equal to mu naught by 4 pi into I dl sin theta divided by r square. So this is r. Now it is the radius. Radius itself is shortest distance, no? Radius itself is going to become shortest distance now. So d and r are same now. Now what is sin theta? See, what is theta angle? 90 degree. Therefore this will become 1. So that is equal to mu naught by 4 pi into I by r square into dl. Therefore mu naught by 4 pi is a constant. Then I by r is a constant. R square is a constant. So only variable is dl. So integrate now to get the total field. Integral of dB equal to b. Integral of 0 to 2 pi r, isn't it? Therefore mu naught by 4 pi into I by r square into dl. So that is how much? Integral of dl is circumference, that is 2 pi r. Therefore mu naught by 4 pi into I by r square into 2 pi r into 2 pi r. Therefore pi cancel, 2 times gets cancelled, r square cancel. So what is the field at the center of a current carrying loop? So B is equal to, we can write B is equal to, at the center of a current carrying loop, what we have finally? Mu naught I by 2r. Mu naught I by 2r. Mu naught I divided by 2r. Mu naught I by 2r. So that is our field due to a current carrying loop at its center. This is our third very important formula, and from this we will get one general formula now. General formula, that is, suppose we have an arc of circle. Suppose we have an arc of a circle. Okay. So we have an arc of circle here. There is one arc of circle. Field due to arc of circle. Means we are taking one arc now. One arc of circle we are taking now. This is this. It's an arc of circle and it is making an angle phi at the center. Right. So in this case we are going to get B at the center is equal to mu naught by 4 pi into I by r into phi. Phi is the arc angle at the center of the circle. Therefore, this is a general formula that we can use to find for any circular arc. For for any circular arc, we are going to use this one. This is our general formula. We need not remember different formulae. Now apply that. Take a circle now. Take a circle. What is phi for a circle? 2 pi. So what you will get? Mu naught I by 2r or not? Mu naught I by 2r. Semicircle, pi. Semicircle, pi. Pi gets cancelled. Mu naught I by 4r. Quarter circle, pi by 2. So any circle or arc of circle, we can use this formula. Only single formula. So how many you have to keep in mind? Only 3 so far. First one, mu naught by 4 pi I by d into sin alpha plus sin beta. Infinity conductor, mu naught by 4 pi into 2i by d. Next, circle, arc of circle, mu naught by 4 pi into I by r into phi. Into phi. Only three formulae, if you keep in mind, you can solve most of the problem. All the problems, not most, all the problems. But now, when it is a circular loop, what is the direction of magnetic field at the center? That is very important. So, magnetic field at the direction of magnetic field at the center of a current carrying loop. At the center of a current carrying loop. So, direction of B, direction of B at center of circular loop, center of current carrying loop, current carrying loop, right. Now let us take two currents, clockwise, anti-clockwise. We take both. First we will take clockwise. So we are taking clockwise. First we will take clockwise. So this clockwise current here, and next anti-clockwise current. Two currents we are taking now. Here this is clockwise and this is anti-clockwise, I. So I. Now, what is the field at the center? What is the field at the center of the circular loop? Again, for this also, we are going to use our right hand palm rule. Here, you imagine that you are holding the ring in your hand, in your palm, like this. Keeping the thumb stretched. Keep the palm like this. Imagine that you are holding the ring in your hand. But the fingers should be in the direction of current. See, for example, clockwise current. See now, I am imagining like this. This is my ring. This is the ring. So current is carried in the clockwise direction. This is my ring. So I am imagining that this ring is kept in my palm and my fingers are in the direction of curled, means in the direction of current. Is it clockwise or anti-clockwise? Clockwise. Then this direction of thumb will indicate the direction of the field. See, when it is clockwise current, how the field will be? When the current is clockwise, you hold like this. Current is clockwise. See how the field? The thumb indicates the field. Away from us. That is, it will be into the plane. The field is into the plane. into the plane. Next, take anti-clockwise. Anti-clockwise, see, anti-clockwise. Anti-clockwise means what? It has to come like this. Anti-clockwise now. This is clockwise, just take opposite anti-clockwise. When it is anti-clockwise, see, anti-clockwise, my finger is coming towards me. That means here the field is out of the plane. Here the field is out of the plane. So the field is here out of the plane. See this. It is out of the plane. Means it is coming towards us. So clockwise current at the center into the plane, and anti-clockwise out of the plane. Out of the plane. So anti-clockwise current and clockwise current. So that three, if you remember, that is more than enough for us. Straight current I told you, and circular current I told you. Now, not only that, one more easiest way to remember this direction, see, when you take a coil carrying current clockwise, that coil will behave just like south pole of a magnet. South pole of a magnet. So see this. It will behave like south pole of a magnet. South pole of the magnet. See this, like this. See this? How? Clockwise, no? It is coming like this. South pole. It is south pole. Whereas, when you take current anti-clockwise, it will behave like a north pole. The face of the coil will behave like a north pole, like this. Just see this. North pole. It is just like a north pole. See, anti-clockwise, anti-clockwise. So this is behaving like north pole, and this will behave like south pole. So a current carrying loop that carries current in the clockwise behave like a south pole, and that carry anti-clockwise current is going to behave like a north pole. So that 4 points you have to keep in mind. So 3 formulae and 2 direction for straight current. As I told you, suppose if you take this is the straight current, conductor carrying current, this is the straight conductor carrying current, then if it is going to be here upward direction, I is carried in the upward direction. I in the upward direction, then field to the left is out of the plane. Field here is out of the plane. Sorry, here out of the plane, and here into the plane. So out of the plane we put a dot in a circle, and into the plane we put a cross like this. So upward current is like anti-clockwise current. But now if it is clockwise current, means downward current. If it is going to be downward current now, we are taking here downward current. This is the downward current now. I is in the downward direction. Now you take right hand palm rule, keep like this. You are assuming that you are holding the conductor like this with the thumb in the direction of current. Then it will be opposite to that. See? Here it is coming out of the plane. The field is coming out of the plane here. Field is coming out of the plane. Here it is coming out of the plane, and here out of the plane, and here it will go into the plane, just opposite to this. Just opposite to this. See the field, that the direction of field. So B vector, and this is also B vector, direction. Already we know the magnitude, so this is the direction, and here these are the directions. So clockwise current, clockwise we write CW. Generally we don't write every time clockwise, we write CW, clockwise. Anti-clockwise, ACW. So anti-clockwise current loop behave like a north pole and clockwise current loop behave like a south pole. So these are the points that you have to keep in mind related to Biot-Savart's law, finding out the magnetic induction by using Biot-Savart's law, right? So tomorrow, based on this, we are going to solve different types of problems, right?